Okay, so today I want to finish up the topic of data structures for strings, because, well, although we've seen some nice stuff that is theoretically cool, strings themselves are practically very important. So string searching and string data structures are very important. And what I'd like to show you today is more on the practical end of the spectrum. So they're not the theoretically fastest running times, but they are, well, they used to be what was pretty much the standard data structures for storing and indexing large strings. A little bit more modern data structures exist now that work on compressed strings, but if you want to learn about those compressed string data structures, those compressed representation, then you need to know all this stuff too. So this is a good leaping off point if you want to read further. Okay, so last class we had we looked at the suffix array, which stores all of the suffixes of a string in sorted order, or at least it represents them as a permutation. And I said, in addition to the suffix array, there's also this LCP array, which stands for longest common prefix, which can be used together. The suffix array and the LCP array you can use to build a suffix tree in linear time. It turns out, though, that in practice, the suffix array and a version of the LCP array are so nice and compact, and searching just with those is so fast that you don't bother building this tree-based data structure, this suffix tree. So I'll talk a little bit about this LCP array and its uses. And how that works. So first we'll start with, let's say we have a set S is S1, S2, up to Sn is a set of strings. And we'll use the convention that S1 is lexicographically before S2, which is lexicographically before S3, and so on, all the way up to Sn. So if we were to sort those strings in lexicographic sorted order, so alphabetic sorted order, dictionary order, then that's the order that they appear in. Then I'll say that LCP of I is equal to the length of the longest common prefix of SI and SI plus 1. And that makes sense for any I equal 1, 2, 3, all the way up to n minus 1. And LCP of n, we'll just define that as 0, because the longest common prefix of Sn and nothing comes after it is, we'll use the convention that it's 0. Okay, so just so it's clear what we're talking about, if this is my set of strings, Ali, Alice, Anna, Elias, and Eliza, then what's in the LCP array, right? So this is my string, this is S1, this is Sn. Then the LCP array will have well, the length of the longest common prefix between S1 and S2. The common prefix is ALI. So there should be a 3 there. Between S2 and S3, well, these ones differ in their second character. So there's a 1 there. S3 and S4, those differ in their first character. So there's a 0 there. S4 and S5, they agree on their first 3 characters, ELI. And then the last one, by definition, is 0. Okay. So this is LCP1. This is LCP-N. Okay. That's clear? Good. And one thing you can notice, so that's one thing. I'll write this when it's just a little I. It just means the string I and the string I plus 1 that comes after it. But it'll also be handy to write something like LCP SI SJ, which the definition is it's equal to the longest common prefix of SI and SJ. But it also happens to be the case that that's equal to the minimum of the longest common prefix of SI and SI plus 1, longest common prefix of SI plus 1 and SI plus 2, all the way up to the longest common prefix of J minus 1, SJ minus 1, and SJ. Okay. Right, so just think about that. I have SI and SJ, and if I tell you that those things agree on this many first characters, well, here's SI plus 1. Lexicographically, it's between SI and SJ, and if I compare SI and SJ, they're all equal up to this character, which means that SI plus 1 and SI must also be equal up to this character, or else, or else that, I mean, it would have fallen out here or up here, okay? And so really, the longest common prefix between SI and SJ is just the minimum of all those prefixes, one after the other. Okay, quite easy. All right, and just one thing that I'll point out is there's a connection here between something that we've seen before, which is that if I give you, let's say, this array of these values here, then there's a data structure you can build that uses linear space, and you can build it in linear time that will let you answer longest common prefix queries for any SI and SJ by using the fact that it's equal to the minimum of these values, right? We've seen a range minimum data structure that takes an array of integers, and for any I and j can tell you the minimum in the subarray I to j. Okay, so from this you can answer these things if you use a range minimum structure. We'll see that in actuality you don't even need that, but it's good to know. All right. So what can we do with this longest common prefix structure? Or this longest common prefix information. So one thing we want to do with sets of anything is to search in them, right? So you might give me a string S and say, well, I want you to find S in this set, or if you can't find it, show me the things which are closest to S, meaning the largest string which is smaller than S, or the smallest string which is larger than S. And, well, of course, if you have these in sorted order, you can do binary search, but there is a problem. Well, it's not a problem. Binary search works fine, and it takes O of log n steps, but each step involves comparing S to one of the strings in this set, and the time to compare two strings depends on the length of their longest common prefix. In fact, it's exactly the length of their longest common prefix plus a constant. So you have to do exactly one more comparison than that. And actually, so the only thing you can say in general is, well, that's no longer than the size of that comparison is at least over by the time you reach the end of S. So you get the size of S times log n. And that sounds crazy, right? Like if you compare some string to some random string, then it seems like you're going to resolve the comparison much sooner than having to look at all of S. But what binary search does is it keeps narrowing down the range for S to strings which are closer and closer to S, meaning that they actually match more and more characters of S typically. So towards the end of this search, I mean, it really depends what strings you have, but it kind of puts you in a situation where the comparisons take longer and longer as the search gets closer and closer to the answer. In fact, the final answer, if S is in the set, will take length of S to compute. Okay, so let's see if we can use this LCP array, because this comparison between S and something in our set seems to depend on the longest common prefix between S and the thing we're comparing it with. So let's see if we can use this information to make this search faster. So a typical stage in a binary search, you have the range narrowed down to some subarray. You know that the string you're searching for is, let's say, bigger than Si, or maybe bigger than or equal to Si, and less than Sj, or maybe less than or equal to Sj. So it's somewhere in this range here. And the binary search then goes right to the middle of that and does a comparison with your string that you're searching for against whatever's in the middle here. And M is just something like I plus j over 2. I don't know. Take the floor. All right. So it turns out that if you have access to this information, you can do things faster. And the strategy is the following. So I will keep track of the length, this thing here, which I'll call L, is the length of the longest common prefix from between S and Si. So L is for left. And I'll also keep R, which is the length of the longest common prefix between S and Sj. Now, I would like to use this to speed up the comparison between S and Sm. And so that's one thing that I hope that it's useful for. But at the same time, I have to also guarantee that after I've done this, I now know the length of the longest common prefix between S and Sm. Okay. And in such a way that somehow I'm saving something. Okay. So let's look at the things that can happen. I'll try and so for now, I mean, we'll assume that L is less than or equal to R, like in this picture. It's symmetric if it's the other way around. So what do we know about the longest common prefix between SI and SM? So if I look at S looks like this. It starts with R values that match everything in SJ, and then there's some other stuff. And the first L of those R values match everything in SI, which means that the first L values in SI match the first L values in SJ. All right. So we know for sure that if I ask what's the length of the longest common prefix between SI and SJ, it's something that's bigger than or equal to L. Okay. So what are the possibilities? So if the longest common prefix of SI and SJ is bigger than L, so they don't just match in the first L parts, but they also match at least one more character, then, well, what can you tell me about where S is in that picture?
It should be slightly closer to S1.
SI?
Yeah.
Okay, so let's see what that means. So we have S, and since our binary search has gotten here, we know that S is bigger than SI. Okay, but SI and S, they disagree right here, right? So whatever this character is in S is bigger than this character here. Now, if these guys and these guys, or yeah, I mean, it's definitely bigger than. So if these guys agree on this character, so it's the same character here, well, then it looks like something's wrong, right? Is that possible? Right. So S agrees with all of these things up to this character and doesn't agree with this one, but that's not possible. Okay. So it's definitely not the case that the longest common prefix of SI and SJ is bigger than L. It's not a possibility. Okay. All right. So otherwise, let's say that we look now at the longest common. Sorry. I made a mistake. What I want to look at is the longest common prefix of SI and SM. So I'm going to look at the longest common prefix of this one and this one. Now, if that's bigger than L, then that means these things agree on the first L things, and they agree on at least one more character. And we already figured out that S is bigger than SI because it's bigger than, well, you figure out that it's bigger than SI by the time you get to this character, which means that if I do the same thing to SM, I know that S is bigger than SM. Okay. So if that happens, then S is bigger than SM. Good. So S is going to be somewhere in this range. We know that we're going to recurse on this part and this part. And now all we need to do is figure out what the length of the longest common prefix is between S and SM. We need to know that because that's what we're assuming we know at each step in the algorithm, the longest common prefix between the left side and the right side. And we do that by starting at this character of S and this character of SM and comparing them until we find the first place where they're different. So we learned something about it like so. Okay. How long does that take? Well, it takes as many characters as they agree on. I don't know what that is, but let's just notice that when this happens, I went from a situation where I had L and R, and now I have L plus something. I don't know, T, where this is the time it takes me to check these things. Okay? And in particular, the smaller of these two numbers, L or R, the smaller one was L, just got bigger by T, and the time it took me to do that was O of T time. Okay? So, and that's what's going to keep happening is we're going to recurse on something, we're going to spend T time, and the smaller of the two numbers is going to go up by at least T. All right. All right, so that's the first case.
Can we say that T equals R minus L?
Can we say that T is equal to
R minus L?
No, no. No, we don't know that because T could be even equal to 0, right? So it could be that SI and SM agree on their first L plus 1 characters, which means that these things differ at exactly the same spot. So we find out immediately that that's the case, the first letter we check, but then L doesn't go up at all in the next round. Okay. All right, so that's the first case. Otherwise, we're going to look at LCP of, okay, and I should mention that, of course, the LCP of SI and SM is at least L. That's because right, these the first L letters here are equal to the first L letters here, which means that the first L letters of everything are equal to the same thing, including SM. So we don't have to worry about the case SI SM is less than L. So now we know that LCP of SI and SM is exactly equal to L. So these two are the same. Something different is happening here. So now we're going to look at the LCP of SM and SJ. And let's say that that's K. And K could be, well, it could be bigger than or equal to R, or it could be less than R. So let's assume that it's less than R. So I look at the LCP of this and this, they agree for some number of additional characters, but not as much as R. So that means that when I compare S, I match, 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 and then there's a difference here. Now, where is the search going to go at this point? Do I know if S is over here or if it's over here? Has to be on the right-hand side. Why? Because SM comes before SJ, which means that this X here is smaller than, right, they differ right here. This X is smaller than whatever this X prime is here at the corresponding location here. So this one is smaller, this one is bigger, and S itself actually has an X prime here, so it's bigger than this one. Okay. So if that happens, then we know that S is bigger than SM. And again, so we're going to be working on this side, and the time that took us was whatever number of characters, extra characters we matched here, these T characters, but the length of well, the left side in this case increased by T again. All right. And well, then the last case. If these guys match SM and SJ match at least for the first R characters. Okay. So, and in general, all right. So now I will still be comparing SM to S, starting at position L. I'll do that for these T steps until something different happens. Even better than that. If this is the case, then I don't need to do that comparison starting all the way back from L. Why not? Because, so L is back here. I know that the first R characters here agree with the first R characters here. That means they all agree with S. So I can start at position R, because everything else agrees with S, and start counting off characters until I find a difference. Now I don't know if the search is going to go on this side or on this side, but it doesn't matter because the number of characters I had to look at was T, and in either case, the length of one of these two things goes up by T. So if I recurse on this side, it's great. It goes up by even more than T. But even if I recurse just on this side, well, then the one on the right increased by T. So I have these two prefixes, this L and R, that at each step I do order T work, and one of them increases its length by at least T. And neither of them can ever get to be bigger than the length of S, right? So that means over all the iterations, so I have these two numbers, L and R, and at each step, either L goes up or R goes up, or maybe they stay the same, but it only takes constant time. But the point is that the work that I spend making them go up is not more than 2 times S, 2 times the length of the string that I'm searching for, because neither of these could ever get bigger than the length of S, because they tell you how much of S matches with the string on the left and the right. Okay, so what does that mean? That means that at every round of binary search, I do some amount of work that drives one of these things up by the same amount of work. And then once that's done, the size of the set that I'm searching on is reduced by a factor of 2. Okay, so that means that the number of rounds is log n, and the number of time that I spend over all rounds increasing the values of L and R, which is just doing comparisons here, is only 2 times the length of S. So it's log n plus the length of S. Okay. So if you have one of these LCP structures that lets you answer what's the longest common prefix of SI and SJ, then you can use that to speed up your binary search. So instead of the size of S times log n, it's the size of S plus log n. Okay. Yeah. Okay, so the question is, if I want to build this this longest common prefix structure, how do I do so? Well, the heavyweight way to do it is to build this thing, which I'll explain how to do in a minute, and then build a range minimum structure for this thing. That lets you answer longest common prefix queries in any amount of time. The more clever way to do it is to think about, well, what kind of queries is it that you're going to want to answer? Because I'm always querying SI, SJ, and it's either SI versus SM or it's SJ versus SM. And if you think about the way binary search runs, that means I only need to know. I mean, binary search starts with the first thing. I mean, this is I, this is J, this is 1, this is N. And the first M is going to be N over 2, basically. So to do that first step of binary search, I need to know the longest common prefix of S1 and SM, and I need to know the longest common prefix of SM and SN. That's only two values to store. So I need to store a value here and a value here. And then the binary search is going to recurse on this side, or it's going to recurse on this side. And on this side, there's 2 values that I need to know to answer the 2 queries that could come up. On this side, there's 2 values I need to know that to answer the 2 queries that could come up, and so on. And so actually, if you think about it for a while, you'll realize that there's actually only, well, the number of leaves in this tree is n. And in fact, you can only go down to the pairs. So if you think about it for a while, you realize actually there's only about n different queries that you need to know the answer to. And you can compute those easily by starting from the leaves of this tree, working on the pairs and working up. Okay? So you don't need a full range minimum query structure, because you're never going to ask a question like, what's the longest common prefix from between this string and this string? That just doesn't happen in this algorithm. Okay. So there's basically an array. If you do this carefully, there's an array of length n, which stores all of these queries. When your next step in the binary search, you know exactly which array location has the answer that you're looking for. All right. So that's one thing. That's how much you have to store, and how you can get it from this list, this list here, this sequence here of numbers, just by pairing them off, basically, and making a tree out of that. But how do you get this sequence of numbers, the one that tells you the longest common prefix between one string and the string that comes next in sorted order? And even more importantly, well, how do you get this? If you have a set of strings, how do you get them in sorted order? Well, it turns out that you can just use something we've seen before, at least two different ways. And that is just string quicksort, whose recursion tree happens to be a ternary trie. So what is string quicksort? In string quicksort, you pick a random string. So it's going to be one of these guys uniformly at random, Si. You compare the first character of every string to the first character of the string you just picked. And that first character is either going to be smaller, or it's going to be bigger, or it's going to be equal. And well, that's to sort now. I need to recursively sort this side. I need to recursively sort this part, but actually not everything in this part, because everything in this part starts with the same first character. So I recursively sort here, but ignoring the first character. And then I need to recursively sort this side. And actually, I mean, that's the quicksort algorithm sort of with ties. And the only difference, I mean, if you do the same analysis that you do for quicksort, what you'll realize, or what you'll find out, is that the running time of that is O of n log n plus the sum of the lengths of the strings, which is about the best you can do for comparisons. You can't avoid n log n comparisons. And well, this just says that you have to look at every string. I mean, you have to completely look at every single string in your set in order to sort them. Okay. So that's how you can get this thing in sorted order in this length of time. And the LCPs, you can actually, so you don't explicitly build it, but if you look at one of these ternary tries, in particular, if you look at a path in one of these ternary tries, you can associate with every node an integer which is the number of times the path goes down the middle child. Right? So this one is 0, this one is 1, this one is 1, this one is 2, 2, 2, 3. And why would you want to do that? Well, the reason you want to do that is because every string that you will store in this subtree, of course, all the strings that you store down here, they start with the same first three characters. Right? You know, you came down here because this was an M. You came down here because this was a R, and you came down here because maybe this was an O. So all the strings down here start with MRO. All right. So that means any two strings in this subtree have an LCP which is at least 3. And to get this sequence here of always the LCP between Si and Si plus 1, you can do that just by doing an in-order traversal of this tree, right? So you know how to walk around a tree, visiting the nodes in order. And all you have to sort of keep track of while you're doing this is the depth of this magic number here of the common ancestor between Si and Si plus 1. That tells you the length of of their longest common prefix. And you don't actually need to build this tree. All of this information is hiding inside the quicksort algorithm if you keep track of it while you're recursing. So when you recurse on here, you remember that, okay, the depth of this node is 1. When you recurse on here, you also remember that it's 1. Down here, you remember that it's 2. And you'll be able to actually to get that just out of there. So there's no need to build the tree. You just use the recursive quicksort algorithm, carefully keeping track of the depth of things. And while doing that, you can pull out these things here. All right. Okay. So that's all fine and dandy. That's a way for us to sort a set of strings fairly quickly, n log n time plus the total length of the strings, and at the same time to build this LCP array. So notice, while doing this, we're basically just creating 2 arrays of integers. One of them is to tell us the sorted order of the strings, and the other one is to tell us the LCP. So this is just 2 arrays of integers, each of length n. Now, we made a big deal last class about constructing this suffix array. And what was the suffix array? Well, the suffix array was a sorted set of strings, but it wasn't just any sequence of any set of strings. They were S1 less than S2, S3 less than Sn. They were all the suffixes of some string, and things get messy here. I will call it S, and that string should have characters. Those characters, I'll call them S at 1, S at 2, all the way up to S at n. Okay. And the classic example is take the string S is equal to banana. And when I sort all of its suffixes, I get the empty string, the string that has just the letter A, Anna, okay, good. So if this is my string S, then S1 is the empty string, S2 is the string with an A, S3, and this is Sn. And of course, the suffix array doesn't store these strings explicitly like this. Each one of these is just an index into this thing here. Now, let's look at the LCP values. Well, the LCP values here are this one and this one differ in their first character, so that's a 0. This one and this one agree in one character, then they differ, so that's a 1. This one and this one agree in their first 3 characters, so that's a 3. This one and this one differ immediately, that's a 0. This one and this one differ immediately, that's a 0. But this one and this one agree in 2 characters, and this one by definition is a 0 because there's nothing after it. Okay, that doesn't tell me much. So I claim that we can figure all of this out. I mean, we spent a good deal of effort to get these suffixes in linear time. It would be a shame if to compute these LCP values, we have to spend more than linear time. So I claim that we can actually get this sequence of LCP values in O of n time. And let's see if we can work through that slowly and carefully so that we can remember it for at least 5 minutes after the class is over. And I think the picture that's going to guide us all, that's going to help us do this, is to look at this thing. $. We'll write it this way, and we'll write the LCP values alongside. So down here, I'll write the LCP value for banana. Where's that? There's banana. Its LCP value is 0. Anana. Its LCP value is also 0. Nana, that's the one that's 0 by definition. Anna, that's a 3. Na is a 2. A is a 1. And then this one is a 0. Notice anything? So somehow from this picture, we're supposed to figure out a linear time algorithm. From this example, we should be able to figure out a linear time algorithm to compute these things. So you don't have to say anything deep. Just, do you notice anything about this particular sequence? Yeah. It's a bunch of, okay, so if you go this way, it's increasing. Yeah. And in particular, this 3-2-1 thing is kind of interesting. And so one sort of property that I can say, sort of weak thing, is if I look at any number that's not 0, then the number that comes after it, well, is 1 less in this example. Is it always going to be 1 less? Let's see. So
I think then we're going to have a problem from 0 to 3, right?
So from 0 to 3, somehow there's a big jump here. But then from 3, it only goes down by 1. From 2, it only goes down by 1. And from 1, it only goes down by 1. But from zeros, there seems to be these jumps. And maybe there's other jumps too. But somehow one thing that I can notice is, well, the jumps up, there's a big one right there. It jumps up by 3, but the steps down, they're never more than 1. So let's see if we can convince ourselves that somehow that's not just by accident. So let's take a look at, we take SI and SI plus 1. Now, the LCP of I tells us how much these strings agree. And it says they differ for a while. Okay. So I know that SI and SI plus 1, they differ by that and that. Okay. And what is SI? Well, SI is the string that starts here at position I and goes to the end. Oh, sorry, no, that's not true. It's a string that starts somewhere. I'll say position X and goes to the end. So this thing here is the string SI. It's all that. It just happens to be that in sorted order, this one comes out in position I. SI plus 1 is some other one. I don't know if it comes before or after, like if it's to the left or right here. It's just some string that starts at some position Y. Okay. But LCP at I is telling me that, yeah, this thing is equal to this thing for exactly this many locations. The length of this is LCP of I. In fact, I should be more careful. This is, yeah, this is LCP of I. Okay. Now, what can you tell me about this thing? If I just take the first character off of SI, that's the thing that comes next here, right? That's this guy here. What can you tell me about the LCP of that thing? Can it be big, small? Well, I know that there's a string, another string in my set that agrees with this one. So this thing here is called, so this is position X plus 1. So it starts here. It has all of these same characters. I know there's another string in my set, namely the one that starts at position Y plus 1, that agrees with those characters. Okay. So that means, let's try and be careful here, that the LCP of I. So this thing here is the LCP rank X. So if I look at there's a string that starts at position X and goes to the end. Its index I is equal to this rank that we talked about last class. It's the inverse of the suffix array. So that's what we're looking at here. The LCP of the string whose rank is X is the LCP of this string I. So that's one thing we've got. And we're also looking at the LCP of the rank of X plus 1. That's this string that starts here at a position X plus 1. And so this is S sub rank of X plus 1. The LCP of that thing is at least as big as the LCP of this thing minus 1. Okay. All right. Now, the claim, though, was that it was equal. And if I look at this example here, it always is equal. I have, right, the LCP of the string starting here at n is is exactly 1 less than the one that starts here at a, and this one is exactly 1 less than the one that comes before it. Is it necessarily true that they're always equal? Yeah. So all I know is that, I know this inequality is true because I can see there's another string that agrees with this one on this many characters. But there could be other strings somewhere else that agree with this one on more characters, right? So if this was, let's say, a dot character, this was a dot character, there could be another string that is a box character followed by a whole bunch of stuff which agrees with this one even longer than this one does. So all I know for sure is that this LCP value does not go down by more than 1, but it could go up. It could shoot up. Well, here it goes up from 0 to 3, but it could even go up from 3 to 100. All right. So how is that going to give us a linear time algorithm? Any ideas? Well, let's do it on this example here. I'm going to compute the LCP values in this order. Okay, so I should be careful. This number here is not LCP of 1. It's LCP of this thing here. So this thing here is LCP of, what's this? 1, 2, 3, 4, 5. Okay. But I'll compute them in this order. And we saw that from the suffix array, you create the inverse array that's called the rank array that will tell you, yes, this is number 5, this has rank 5, and so on. So I'll compute, the LCP of this thing in this order, but remembering that this is tied to some rank. Okay. So I already have the suffix array, which gives me things in this order. And initially, I start with no information, just starting with this string. And so from the rank array, I can learn that this string is at this position in the suffix array. And at position I, so this is some position 5 in this case. So at position 6 in the suffix array is the string that comes after this. So I need to compare the longest common prefix of this string and this string, which I just do by the usual way. I see here immediately that they differ in their first character. Okay, so I get a 0. Next comes this thing. I use the rank array so this is anana. I use the rank array to see that that's here. I see it's at position 4. So this is position 4 in the suffix array. I'm interested in comparing it to position 5 in the suffix array. I immediately see that the first characters are different. That gives me a 0. Next comes nana, which is at position, must be 7. That's the last position. There's nothing that comes after it, so that's a really easy one. That gives me a 0. Now the bad news starts. This is Anna. The rank array tells me, here it is. I have to compare this string and the one that comes after it, and I do so. They agree, they agree, they agree, and then they differ. So I get the answer 3. So this is important because it's the first non-zero thing that something interesting might happen. Next, I want to move to na, which the rank array tells me where that is. It's here. And the suffix array tells me the string that comes after it in sorted order is nana. That's this one. Now, I need to compare these things and figure out their longest common prefix. How should I do that? Yeah. So I know because of this, that because the last one that I just computed was 3, this one is at least 2. Meaning that I know without knowing anything else, the first 2 characters of these 2 strings agree. I don't need to compare them. So I then start comparing at this location, immediately see that they differ, and so the answer is 2. And then finally comes A, which is here. I have to compare it to Anna, and I know that these 2 strings, A and what comes after it, agree on at least 1 character because this string and the one that came after it agreed on 2 characters. So these 2 comparisons, I do not start at the first character, I start at the second character. And immediately I see that they're different. And then the same thing happens here. But it's a bit more boring. So I need to compare this empty string and this string. I knew that the previous one I did was 1, so the longest common prefix had length 1, which just tells me nothing useful. It only says that the longest common prefix of this one and this one is at least 0. I have to start again at the first character. Okay. All right. So that's how you do it. You walk through this string in order, computing the longest common prefixes as you encounter them. Using the rank array and then the suffix array to know which things to compare with. And the only extra trick that you use is the fact that, well, if I just figured out the longest common prefix of this one and the one that came after it was k, then this one is at least k minus 1. Now, why should all that run in linear time? Well, let's look at what's happening to these numbers. That's this sequence here. Yeah. So it starts out at some value that we get just by whatever happens when we take the first string and compare it to what comes after. It happened to be 0 for us, but that's not always the case. So it starts out at some number. That's right. So the first string, we have to do some work, and we get that number up to something. Now the next string comes along, and the number drops by at most 1, right? It goes down by at most 1. That's what that inequality told us. And then we have to do some work. And the number goes up by the amount of work that we do. And then that thing drops by at most 1. Right? So the next comparison we are going to do is going to start at this position in the next two strings. And then we do some work, it goes up. And then it drops by at most 1. And then maybe it doesn't go up at all. It just keeps dropping. But this is not work that we have to do. So if I want to do this picture right, the blue stuff is work that we have to do. The white stuff is just stuff that we get for free from the previous value. Maybe it goes back up and then starts to come down again. Okay, so and of course the whole thing we never get a longest common prefix of length bigger than n, right? So we have this number. At each stage, it goes up by something. We have to pay for that. Then it goes down by 1. Goes up by something. We have to pay for that. Goes down by 1. Up by something. So that means we have a bunch of minus 1s. We have n of these minus 1s. And then a whole bunch of these blue things that we have to pay for. But we never get a number bigger than n. So that means that the stuff that we have to pay for never adds up to more than n, right? It can't add up to more than all of the minus 1s. So view that however you like. I use a credit argument or whatever, but it's basically this is what's happening. So we have essentially we have a line of a bit of code where some counter gets decremented once every time we go through the loop, and it gets incremented a variable number of times, but it's never more than n. So that tells us that the total number of increments is never more than the number of decrements. Never more than n more than the number of decrements, which is at most n. All right. And you can look this up. This is it's an algorithm by Kasai and others. So it sounds complicated, and there's a lot to get your head around what we're doing here. But literally, the thing is like 6 lines of C++ code. It's quite simple and very efficient. You just need the rank array, the suffix array, and you're constructing the LCP array. And once you have those two things, the suffix array and the LCP array, you can toss out the rank array. You don't need it anymore. And you can do these searches for any substring in your string, and whatever the length of the time it takes is whatever the length of the string you're searching for is, plus log n. And all of that is indexed using just 2 arrays of integers, each of length n. All right, so that's a good place to leave it for strings, and it's a good place for anybody who's interested in learning more about this to start looking at compressed indices. So compressed meaning you compress the strings, indices meaning you can search on them the same way you can search in these suffix arrays. All right, that's all for today. Yep.
Is that the algorithm that you find a document?
So up until I don't know, up until 15 years ago, basically web search and all of these searching big text databases ran on suffix arrays. So they didn't use Patricia trees because the space for huge amounts of text, the space overhead is too much. I mean, there's all these pointers, there's these arrays in all these nodes, that's too much. Here, you need to store the original text, some string, and 2 arrays of integers, each of which is the same as the length of the string. And the only performance penalty you pay is you pay a plus log n in the search time instead of just the length of the string you're searching for, and that's good enough. And in fact, if you care about real performance, then a plus log n that uses, let's say, good memory access patterns is typically faster than something that chases a lot of pointers around, like you end up with a Patricia trie. So, okay. All right. Thank you.